Picture this. You're standing on the edge of a canyon in Washington state. It's 1915. Below you, 1,000 feet down, a river cuts through rock so steep that no road will ever reach it. And on the other side of that canyon, covering a slope so vertical you couldn't walk up it without grabbing trees for handholds, stands a fortune in Douglas fir. Trees 200 feet tall, trunks 8 feet across, each one worth more than most Americans made in a year. The timber companies wanted those trees. The sawmills in Seattle and Portland needed those trees. The growing cities of the American West were screaming for lumber. But there was a problem. Actually, there were several problems. The canyon was a mile wide. The slopes were 45 degrees or steeper. There were no roads. There never would be roads. And each of those logs weighed between 20 and 50 tons. So how do you move a 50-ton log across a mile-wide canyon with no bridge, no road, and no way to float it downstream? You fly it. This is the story of the men who strung steel cables across the deepest canyons in North America and flew the biggest logs in America through thin air. It's the story of the high climbers, the most spectacular workers in American industrial history. Men who climbed 200-foot trees with nothing but leg spikes and a leather belt, sawed off the top while standing on it, and rode the trunk as it whipped back and forth like a fishing rod. And it's the story of a system so audacious, so mechanically elegant, and so utterly dangerous that nothing like it had ever been attempted before or has been attempted since. The Pacific Northwest in the late 1800s presented a logging problem unlike anything the American timber industry had ever faced. In the Great Lakes region, loggers had perfected their craft over decades. They'd cut white pine and floated it down rivers to the sawmills. The terrain was relatively flat. The rivers ran in useful directions. The trees, while large, were manageable. A big white pine might weigh 5 or 6 tons. Then the industry looked west, and everything they knew became useless. The Douglas firs of Washington and Oregon weren't just bigger than eastern trees. They existed in a different category entirely. A mature Douglas fir could top 300 feet, with a trunk diameter exceeding 12 feet at the base. A single log from such a tree might weigh 60 tons or more. These weren't trees you could drag with horses. These weren't trees you could float in the rivers, because the rivers in the Pacific Northwest ran through canyons so deep and rapids so violent that logs would splinter against the rocks. The Sitka spruce and western red cedar that grew alongside the Douglas fir were nearly as massive. The coastal forests of Washington, Oregon, and British Columbia contain more standing timber per acre than anywhere else on Earth. Conservative estimates suggested 500 billion board feet of merchantable timber, enough to supply the entire United States for 50 years. The problem was getting it out. And the terrain. My God, the terrain. The Cascade Range and the Coast Range had been carved by glaciers and rivers into a landscape of ridges, valleys, canyons, and slopes that seemed specifically designed to make logging impossible. Grades of 40, 50, and even 60% were common. A horse couldn't work those slopes. Neither could an ox. Men could barely stand on them, let alone drag logs weighing as much as a locomotive. The Olympic Peninsula alone contained an estimated 50 million board feet of timber per square mile. But the valleys were so steep, so choked with undergrowth, so impossibly rugged that early surveyors simply wrote inaccessible across vast sections of their maps and moved on. The first logging operations in the Pacific Northwest tried the methods that had worked back east. They failed immediately. In 1853, a logging crew near Puget Sound attempted to skid logs down a steep slope using oxen. They'd built a skid road, laying smaller logs crosswise to create a track. The oxen were hitched to a single Douglas fir log, maybe 40 feet long and 4 feet in diameter. The teamster was a man named Ezra Collins, who'd driven ox teams in the Maine woods for 15 years. He knew his business, or thought he did. The oxen were hitched. Collins gave the signal. The oxen leaned into their yokes. The log didn't move. The oxen strained harder. Collins cracked his whip. The log shifted, then began to slide. And then it began to roll. 12 tons of wood accelerating down a 40-degree slope. The oxen couldn't hold it. The log ran them down. killing 3 animals instantly and injuring 2 men who'd been walking alongside. Collins himself dove clear, but barely. The log continued down the slope, gaining speed, until it launched off a small cliff and shattered against the rocks below. 40 feet of prime Douglas fir, worth a small fortune, reduced to kindling. 3 oxen dead, 2 men injured, 1 day's work. Collins quit logging that same week. He wrote to his brother in Bangor that the western timber was possessed by the devil himself, and that no method used in the eastern woods could tame it. The logging companies tried different approaches. They built flumes, wooden channels filled with water to float logs down the mountains. A flume system might cost $50,000 to construct, representing a massive capital investment, but it could move logs efficiently as long as everything went right. In 1878, the Sierra Flume and Lumber Company built an elaborate system in the mountains of Northern California. 72 miles of wooden channel, following contours, crossing valleys on trestles, dropping in controlled grades toward the mills below. For 3 years, it worked magnificently. Logs shot through the flumes at 20 to 30 miles per hour, arriving at the mill clean and undamaged. Then in the summer of 1881, a log jammed at a curve. The logs behind it piled up. The water pressure built. The flume walls, weakened by years of wear, gave way. 300 logs, a small fortune in timber, scattered down the mountainside. The flume itself was destroyed for half a mile. Repairs took 4 months. The company never fully recovered financially, but the flumes had an even more fundamental problem on the steepest terrain. When grades exceeded 30%, logs could hydroplane out of control, launching themselves out of the flumes like missiles. In 1892, a log broke free from a flume near Snoqualmie Falls, Washington, and traveled nearly a quarter mile through the air before destroying a small cabin owned by a family named Patterson. William Patterson, his wife Elizabeth, and their 3 children had left that morning to visit relatives. Had they been home, they would almost certainly have died. The lumber company paid for a new cabin. It did not pay for the nightmares that haunted Elizabeth Patterson for years afterward, the knowledge of how close they'd come. They tried building railroads directly to the timber stands. This worked on moderate terrain, but the costs were staggering. A logging railroad might require $30,000 per mile to construct, and some of the best timber stood in areas where no railroad could ever reach. The grades were simply too steep. A locomotive that could climb a 4% grade was considered a marvel of engineering. The slopes above the Quinault River Valley averaged 15%. Some exceeded 40%. John Dolbear, a California inventor, had developed a steam-powered donkey engine in 1881 that could drag logs with cables rather than animal power. These donkey engines revolutionized ground lead logging, using a stationary steam engine to wind cable drums that pulled logs across the ground to a central landing. Dolbear engines spread rapidly through the Pacific Northwest in the 1880s and 1890s. They were faster than oxen, stronger, more controllable. A single donkey engine could do the work of a dozen horse teams. By 1895, there were over 200 donkey engines operating in Washington state alone. But the donkey engines had a serious problem on steep terrain. Dragging a log across the ground meant the log was constantly hitting stumps, boulders, and standing trees. The friction was enormous. The cables broke constantly, and on truly steep terrain, a hung-up log could pull the entire steam engine off its foundation. An engineer named Martin Olson, no relation to William Olson, who I'll tell you about later, was operating a Dolbear donkey near Centralia, Washington, in 1897 when his main line snagged on a stump. Instead of the log coming to the engine went to the log. 8 tons of cast iron and steel slid 50 feet down a slope before Olson could release the clutch. He survived, but the engine was wrecked. Olson walked away from logging that day and never went back. By the early 1900s, the logging industry in the Pacific Northwest had reached an impasse. The easy timber, the trees near navigable water or gentle slopes, had been cut. What remained was the timber that everyone had assumed was unreachable. Trees on cliffs, trees across canyons, trees on slopes where nothing wheeled or walked could operate. Some industry observers believed the Western timber boom was over. An editorial in the Pacific Lumber Trade Journal in 1902 declared that the limits of mechanical ingenuity have been reached, and that the remaining old-growth stands would stand for centuries, protected by their own inaccessibility. The industry needed a new approach entirely. The editorial was wrong. What if, instead of dragging logs across the ground, you could lift them into the air? The concept seems obvious in retrospect. If the terrain is too rugged to cross, go over it. But the engineering required to lift a 50-ton log into the air and transport it across a canyon represented a quantum leap in industrial capability. The key insight came from an unexpected source. Mining engineers in the western mountains had been using aerial tramways for decades to transport ore from high-altitude mines down to processing facilities. A cable stretched between 2 points, with buckets or cars hanging from it, could move material across terrain that no road could traverse. The Bleikert tramway system, developed in Germany, had proven reliable at mines throughout Colorado, Montana, and California. The principle was proven, but ore buckets weighed hundreds of pounds. Logs weighed tens of thousands of pounds. Horace Butters was a logging engineer working in the mountains of Northern California in the late 1880s. He'd spent time in the mining districts and had watched the aerial tramways carrying ore. He understood the physics. Tension in a suspended cable follows predictable equations. If you increase the cable strength proportionally to the load, the system should scale. In 1887, Butters designed and built the first true skyline logging system near Navarro, California. His system was crude by later standards, but it established the principles that would eventually fly logs across mile-wide canyons. Butters anchored a heavy cable between 2 points, one high and one low. The main cable, which he called the skyline, remained stationary. A carriage rode on this skyline, a simple frame with grooved wheels that rolled along the cable. From this carriage hung a second cable, the haulback line, which dropped down to the logs. A steam engine powered the whole system, pulling logs up to the skyline cable and then letting them ride by gravity to the landing. The first test was conducted on a spring morning with a log weighing approximately 8 tons. The choker was set, the steam engine engaged, the cable tightened, the front end of the log lifted from the ground, and for the first time in the history of American logging, a commercial log flew through the air. The log traveled 600 feet, crossing a gully that would have taken a ground-based crew 3 hours to navigate. The flight took 4 minutes. Butters knew immediately that he'd changed everything. The log flew, not quickly, not smoothly, but it flew. It cleared stumps and boulders and gullies that would have stopped any ground-based system cold. Within a decade, engineers across the Pacific Northwest were experimenting with variations on Butters' design. They added complexity. They increased scale. They pushed the boundaries of what steel cables and steam power could accomplish. But they all faced the same fundamental challenge. To make a skyline system work, you needed 2 things. You needed towers at each end, high enough to lift the logs clear of obstacles. And you needed cables strong enough to support 50 tons of wood, plus the weight of the carriage and rigging. Steel technology had improved dramatically in the late 1800s. Wire rope, made by winding individual steel wires around each other in a helical pattern, could achieve breaking strengths that solid steel bars couldn't match. By 1900, a 1-inch diameter wire rope could support loads of 40,000 pounds or more. 2-inch rope could handle loads approaching 100,000 pounds. The cables were there. The question was the towers. Building wooden towers worked in some locations. A crew could construct a 70 or 80-foot tower from heavy timbers, anchor it with guy wires, and rig cables from the top. But building a tower took time. It required hauling heavy timbers into remote locations, often the very locations where roads couldn't reach. And when the timber in one area was exhausted, the tower had to be abandoned. You couldn't move it. Then someone looked at the trees themselves. The idea was so simple that it seems inevitable in retrospect. Why build a tower when nature had already built thousands of them? A 200-foot Douglas fir, properly rigged, could serve as a spar tree, the central tower of a skyline logging system. And when you were done with one area, you simply rigged a new tree in the next canyon. The first documented use of a standing tree as a logging spar was by a man named A.E. Munch, working in the forests near Kalama, Washington in 1898. Munch was an engineer with Weyerhaeuser who had grown frustrated with the time required to build wooden towers. He looked at the massive Douglas firs surrounding his operation and realized that God had already provided all the towers he would ever need. But to turn a living tree into a spar, someone had to climb it. Someone had to strip every branch from a 200-foot trunk. Someone had to saw off the top of the tree while standing on it. Enter the high climbers, the most extraordinary workers in the history of American industry. The name doesn't do justice to what these men actually did. A high climber didn't just climb trees. He performed an act so physically demanding, so technically precise, and so absolutely terrifying that even experienced loggers watched in disbelief. I've read firsthand accounts from men who witnessed high climbers at work. They describe it the same way, over and over. It didn't look possible. It didn't look like something a human being should be able to do. Here's what a high climber actually faced. He'd stand at the base of a tree that might be 200 feet tall, the trunk 8 feet in diameter at the base, tapering as it rose until it was perhaps 18 inches at the intended cutting height. The tree would have branches, hundreds of them, starting 50 or 60 feet up and continuing to the crown. He wore climbing spikes, curved steel gaffs about 2 inches long that strapped to his boots. He wore a leather belt, maybe 4 inches wide, with a rope attached that would loop around the trunk of the tree. He carried an axe, a saw, and a small toolkit. Nothing else, no safety harness, no backup system. The only thing keeping him from falling 200 feet was his ability to keep those spikes dug into the bark. He began climbing. Plant a spike, shift your weight, plant the other spike, shift again. The rhythm had to be precise. If you pulled your spike out before your weight had transferred, you'd slide. If you slid, you might catch yourself or you might not. The bark on a Douglas fir is deeply furrowed, up to 6 inches thick, and offers good purchase for the spikes. But after decades of growth, the bark could also be loose in places, ready to flake off under load. As he climbed, he cut. Every branch had to be removed, because every branch was in the way of the cables that would eventually be strung from the top of the tree. He'd hook his cutting rope around the tree, lean back against his belt, and swing his axe. Branch after branch, some of them thick as a man's thigh. The branches fell around him, crashing through the lower limbs, tumbling to the ground far below. The axe work alone would exhaust most men. Each branch required 5 to 20 strokes, depending on its thickness. A tree might have 150 branches that needed removal. That's over 1,000 axe strokes, delivered while standing on spikes 200 feet in the air. Climbing and cutting, an hour, 2 hours. The ground crew watched from below, growing smaller as the high climber rose. At 100 feet, the men on the ground looked like toys. At 150 feet, the tree began to sway in the wind, a movement barely perceptible at the base, but significant where the climber worked. And then he reached the cutting height. This was determined by the engineers who'd surveyed the terrain and calculated how high the cables needed to be, usually somewhere between 150 and 200 feet, sometimes higher. In extreme cases, high climbers top trees at 250 feet or more, heights at which even experienced climbers reported vertigo and disorientation. Well, now came the most dangerous moment in what was already the most dangerous job in American industry. The high climber had to cut off the top of the tree while standing on it. He'd select his spot, usually where the trunk was about 18 inches in diameter. He'd secure himself as well as possible, which wasn't very well at all. And he'd begin his undercut, chopping with his axe into the side of the trunk, facing the direction he wanted the top to fall. The chips flew. The trunk weakened. The top of the tree began to lean, almost imperceptibly at first, and then he'd move to the opposite side and begin his back cut with his saw. This is where things got complicated. A crosscut saw, the tool of choice for this work, was typically 6 feet long. 2 men normally operated such a saw, one on each end. The high climber worked it alone, pulling and pushing with one arm while bracing himself against the tree with the other. As the saw cut deeper, the top of the tree would begin to go. The wood fibers would start to tear. The climber had to judge exactly when to stop cutting and exactly when to get the hell out of the way. Because when that top went, several tons of wood would be falling past him, close enough to touch. If a branch snagged his cutting rope, if his timing was off by half a second, he'd be going down with it. A high climber named Oscar Jacobson, who topped trees in the Grays Harbor region for 12 years, described the moment in a 1936 interview with a WPA writer. "You can feel it start to go," Jacobson said. "The whole tree changes. The vibration comes up through your spikes. You get maybe half a second of warning. That's when you pull your saw out and flatten yourself against the trunk and pray to whatever God you believe in that you've cut it clean." The top would go over with a sound like a gunshot as the wood fibers snapped. It would accelerate as it fell, crashing through the remaining branches, hitting the ground with an impact you could feel through your boots from 500 feet away. But the climber wasn't done, not even close, because now came the whip. When you cut the top off a 200-foot tree, you remove a significant percentage of its weight from one side. The remaining trunk, which has been straight and relatively stable, suddenly becomes unbalanced. It whips back. Then it overcorrects and whips forward. Then back again, each swing slightly smaller than the last until the oscillations die out. The high climber rode that whip. He clung to the trunk with his spikes and his belt while the tree swung back and forth like a metronome, arcs of 10 or 15 feet at the top. Some climbers described it as the most exhilarating experience of their lives. Others described it as pure terror. Most agreed it was both. Jacobson called it riding the bronc. Other climbers used less printable language. When the tree finally stopped swinging, the high climber had to rig it. He'd haul up blocks and cables from the ground crew, attach them to the top of the spar, run guy wires to anchor trees to stabilize the whole structure. This might take another hour or two, working nearly 200 feet in the air, handling equipment that weighed hundreds of pounds. When he finally descended, he'd been aloft for 4 to 6 hours. He'd burned thousands of calories. His muscles would be screaming. His hands would be torn and bleeding despite the heavy gloves, and he'd do it again the next day on a different tree in a different spot because a working skyline operation might use up a spar tree in a few weeks and need another one rigged. The high climbers were paid well by logging standards, $3 to $5 a day in an era when ground workers made $2. But no amount of money could compensate for the risks they took. They died with terrible regularity. Thomas Erickson was 23 years old when he topped his last tree in 1911 near Centralia, Washington. He'd been climbing for 3 years, had rigged maybe 50 spars. He was considered one of the best high climber in Grays Harbor County. On that day, witnesses said his top cut was perfect. The crown went over clean. But as the trunk began its whip, something gave. Maybe a spike pulled free. Maybe his belt failed. No one ever knew for certain. Erickson fell 170 feet. He hit 3 branches on the way down, which probably killed him before he ever reached the ground. He left behind a wife named Hannah and a 2-year-old daughter named Louise. His daily wage had been $4.50. James Mulligan died in 1908 near Aberdeen, Washington. He just completed his back cut and was trying to get clear when a branch from the falling top caught his climbing rope. He went over with the top, tangled in his own equipment. He was 19 years old. His father, who worked as a choker setter for the same company, saw his son fall. He never worked in the woods again. Carl Johansson had been a high climber for 11 years when his luck ran out in 1916 near Raymond, Washington. The longest-serving high climber anyone knew of. He fell from 140 feet when the bark he'd planted his spikes in sheared away from the trunk, 11 years without a serious accident, and then one bad patch of bark ended everything. He was 38 years old, with a wife and 4 children. I've searched the records for a complete accounting of high climber deaths. It doesn't exist. Nobody kept comprehensive statistics. The logging companies didn't want to know, and the government didn't require them to find out. Best estimates suggest that between 1890 and 1940, during the golden age of skyline logging, Hundreds of high climbers died on the job, maybe more than 1,000. We simply don't know. What we do know is that the spar trees they rigged made possible a logging system of unprecedented scale and capability. Once a spar tree was topped and rigged, it became the center of an aerial logging operation that could harvest timber from terrain that no other method could touch. Cables radiated from the top of the spar to the surrounding hillsides. A main line, the skyline, stretched from the spar to an anchor point as much as a mile away, crossing canyons, spanning ravines, climbing slopes impossible for any wheeled vehicle. A carriage rode on the skyline, a heavy steel frame with wheels that ran on the cable. From this carriage hung a second cable, the choker line, which dropped down to the logs. When a faller had dropped a tree and a bucker had cut it into log lengths, the choker setter would wrap the choker line around the log and signal the engineer at the yarder. The yarder was the heart of the system, a massive steam engine weighing 20 tons or more, driving drums wound with thousands of feet of wire rope. Washington Iron Works in Seattle built yarders. So did Skagit Steel and Iron Works in Cedro Woolley, and Willamette Iron and Steel in Portland, and half a dozen other manufacturers competing to build machines capable of lifting the biggest logs in North America. A typical yarder might develop 300 horsepower, driving drums that could pull 10,000 pounds of load at speeds up to 1,000 feet per minute. The sound was tremendous. The boiler roared, consuming 2 to 3 cords of wood per day just to generate steam. The cables sang as they wound and unwound, sang a high-pitched keening that carried for miles through the forest. The blocks at the top of the spar creaked and groaned under loads that would have collapsed most buildings. When the yarder operator received the signal that a log was choked and clear, he'd engage the main drum. The cable would snap taut, rising from the ground, lifting the front end of the log. The log would come up, nose first, clearing stumps and obstacles that would have stopped it cold in a ground lead operation. If the terrain was right, the log might come completely off the ground, flying through the air on the skyline like some improbable aerial creature. Weyerhaeuser's operations in the Cascade foothills were legendary for their efficiency. Frederick Weyerhaeuser had purchased 900,000 acres of timberland from the Northern Pacific Railroad in 1900, in the largest private land sale in American history to that date. By 1910, a Weyerhaeuser skyline crew might move 100,000 board feet of timber in a single day. That's enough wood to build 8 or 10 houses. A team of 40 men, 1 yarder, 1 spar tree, and a mile of steel cable, matching the output of 100 men using traditional ground-based methods. The logs would ride the skyline to a landing, where they'd be loaded onto rail cars or later trucks. From the landing, they'd travel to the sawmills on Puget Sound or the Columbia River, where they'd be broken down into the lumber that was building the American West. Crown Zellerbach's operations in Oregon pushed the technology even further. They developed multi-spar systems, with logs transferring from one skyline to another, in covering terrain that a single spar couldn't reach. A log might travel 3 miles from stump to landing, crossing 2 canyons and climbing 1,000 feet of elevation, never touching the ground. The Lidgerwood Tower Skidder, developed by the Lidgerwood Manufacturing Company of Montclair, New Jersey, represented the peak of skyline technology. These massive machines could support skylines spanning 3,000 feet or more, with main cables 2 inches in diameter and braking strengths exceeding 150,000 pounds. The numbers tell the story of what these systems accomplished. In 1880, the Pacific Northwest produced perhaps 160 million board feet of lumber annually. By 1905, that figure had reached 4 billion board feet. By 1925, it exceeded 10 billion. The skyline systems didn't account for all of that growth. But they accounted for a significant portion because they unlocked timber that simply couldn't be harvested any other way. But there was another story inside those numbers. A story of what this work did to the men who performed it. Ground crews worked at the base of the spar, setting chokers, guiding loads, maintaining equipment. They made $2 to $3 a day for work that was faster, more dangerous, and more demanding than almost any other industrial labor in America. A choker setter had to work directly beneath suspended loads that might weigh 50 tons. If a cable snapped, if a choker slipped, if the yarder operator made a mistake, there was no time to run. The log would come down, or the cable would whip, and someone would die. I've read the injury reports from the Washington State Department of Labor and Industries. They're clinical documents, bureaucratic in tone, but what they describe is horrific. Crushed limbs, severed legs, decapitations from snapping cables, a 2-inch steel wire rope, when it breaks under tension, whips with enough force to cut a man in half. The reports describe instances where this happened. The words are bland. The reality was unspeakable. A report from August 1917 describes an incident at a wire heuser operation near Mount Rainier. Male, age 34, occupation choker setter, main line parted under load approximately 50 feet from spar tree. Cable struck deceased in upper body. Death instantaneous. The man's name was Peter Lindqvist. He had worked for Wire Heuser for 11 years. He was 2 weeks away from his wedding. And yet, they did it. Day after day, year after year, men reported to the woods and did this work because it paid better than farming, better than fishing, better than most of what was available to working men without education or capital. A choker setter named William Olson worked the Skyline cruise around Aberdeen, Washington for 7 years, from 1912 to 1919. His surviving letters to his brother Eric in Minnesota describe the work in matter-of-fact terms that somehow make it more vivid. Today, we move 4.25 million feet, he wrote in June 1915. Topping jack fell from the spar on Tuesday. Funeral is Saturday. Back to work Monday. That was the rhythm. The logs moved, men died, the work continued. Olson's letters also describe moments of unexpected beauty. Watched the cables this morning before the sun was full up, he wrote in October 1916. The dew on them caught the light. For just a minute, we had a web of silver across the whole valley. Then the yarder fired and everything was smoke and noise again. He survived his 7 years. Many didn't. When he left the woods in 1919 to take a job at a sawmill in Hoquiam, he wrote to Eric that he was tired of counting the missing faces at breakfast. By the 1920s, the skyline systems had reached their peak of development. The technology had matured. The techniques had been refined. Operations were running at efficiencies that would have seemed impossible a generation earlier. And then slowly, the age began to end. Several forces conspired against the skyline systems. The gasoline engine was growing stronger and more reliable. Caterpillar tractors, which first appeared in the 1920s, could work terrain that would have stopped horses, but that wasn't quite steep enough to require aerial transport. They were more flexible than skyline systems, easier to move, requiring less infrastructure. Trucks were improving too. Where the skyline systems depended on railroads to move logs from landing to mill, trucks could use roads that were cheaper to build and could follow terrain that rails couldn't negotiate, and the timber itself was changing. The original old-growth giants, the trees that had made skyline logging necessary, were being exhausted. The second-growth timber coming up behind them was smaller, lighter, more amenable to ground-based harvesting. By 1950, the great age of spar tree logging was largely over. The yarders were scrapped or converted to other uses. The techniques were taught less and less. The high climbers, the men who'd performed the most spectacular labor in American industry, found that their skills were no longer needed. The last of the great high climbers retired in the 1960s. A few continued into the 1970s, working for small operations that still used the old methods. But they were curiosities by then, living fossils of an industry that had moved on. Today, when extremely steep terrain must be logged, helicopters do the work. A logging helicopter can lift an 8,000-pound payload, carrying logs straight up from mountainsides that no cable system could reach. It's faster, more flexible, and doesn't require someone to climb a 200-foot tree and saw off the top. The helicopters are the direct descendants of the skyline systems. The principle is the same. Lift the logs off the ground and transport them through the air. The execution is different, safer, more efficient, less dramatic. But the old spar trees are still out there. I've seen them in the forests of Washington and Oregon, standing among the second-growth timber like monuments. You can identify them if you know what to look for. They're taller than the surrounding trees because they were chosen for height. They're missing their original tops, ending in a distinctive flat profile where the high climber made his cut a century ago, and some of them still bear the marks, grooves worn in the bark by the cables that once radiated from their crowns. I stood beneath one near Forks, Washington a few years ago. The tree was probably 250 years old when it was topped in 1918. It's been growing ever since. Putting on new rings around the old cable scars, slowly healing but never quite erasing the marks of what it was used for. Nobody else was there. The logging road was overgrown. The forest had reclaimed most of the evidence of the operations that once centered on this tree, but the tree remembered. The scars were still visible if you looked. I stood there for a long time, thinking about Thomas Erickson, about James Mulligan, about Carl Johansson, about William Olson, who survived but never forgot the faces missing at breakfast. We drive through the Pacific Northwest now and see forests that look timeless, ancient, unchanging. We see logging trucks on the highways and know vaguely that timber is still being harvested somewhere. But we've lost the connection to what logging once meant, what it demanded from the men who did it, us, what it cost them. The high climbers are all gone now. The last of them died decades ago. They didn't write many memoirs. They didn't give many interviews. They did their work and collected their wages and tried not to think too hard about the friends they'd buried. But what they accomplished deserves to be remembered. They took an impossible problem, timber unreachable by any conventional means, and solved it through ingenuity and courage that bordered on insanity. They climbed trees taller than any building most Americans had ever seen. They rigged systems that flew 50-ton logs through the air. They did it with equipment that was barely adequate, in conditions that would horrify any modern safety inspector, for wages that barely covered their living expenses. The lumber they harvested built Seattle. It built Portland. It built San Francisco and Los Angeles, and 1,000 smaller towns across the American West. Every wooden house in the Pacific Northwest, every barn, every church, every school built before 1950 contains within it the work of men who risked their lives on 200-foot spar trees. I think about Thomas Erickson sometimes, 23 years old, 170 feet up in a tree he'd just topped. Something gave way, and he fell. His widow Hannah got whatever savings he'd managed to accumulate, and a community collection that might have equaled a few weeks of his wages. The timber company got his logs. They got the standing timber he'd helped make accessible. They got the profits from the sawmill and the sales to the lumber yards. His work made all of that possible, and when he died, the work continued without him. That's the story of industrial America in the early 20th century. The story of men who transformed the impossible into the routine, who pushed the boundaries of what human labor could accomplish, who built the infrastructure of modern prosperity with their hands and their backs and their lives. The story of what was gained and what was lost. The cables are gone now. The yarders have rusted into nothing. The landing sites have returned to forest. But if you walk the old logging roads in the Pacific Northwest, if you look carefully at the older trees, you can still see the evidence. The flat-topped spars, the cable scars, the ghosts of an industry that flew the biggest logs in America across the deepest canyons on Earth. They did the impossible, those men. They did it every day, and we have largely forgotten they ever existed. But the spar trees remember. The scar tissue in their bark carries the memory of cables under tension, of logs swinging through the air, of men so high above the ground that the crews below looked like insects. The spar trees remember what the high climbers did, and now, perhaps, so do you.